Welcome back to another Sunrise 2.x tutorial video. Today's topic of discussion will be on how to set up proper safety configurations on your LBR Med robot controller. Before we jump into Sunrise Workbench, let's talk about a few key concepts of the safety: AMFs, PSMs, and ESMs. An AMF is the small unit of safety monitoring. It's called an atomic monitoring function, or AMF. It supplies an elementary level of information. For example, a safety-orientated input that is set, or if the robot is operating in an automatic mode. An AMF is always violated if it is low or in state 0, and it is not violated if its state is 1 or high. So if an AMF goes from high to low, or state 1 to state 0, the AMF is considered violated. A PSM is a permanent safety monitoring function, which is permanently active and uses criteria defined by the AMFs to ensure that the overall system is constantly monitored and safe. The safety function of the PSM can hold up to 3 AMFs, which are ANDed together. The entire safety function is considered violated if all 3 AMFs are violated. The safety functions also define a reaction, which can be triggered if the safety function is violated. Lastly, ESMs, or event-driven safety monitoring functions, make it possible to switch between different safe states depending on the situation. Up to 10 of these ESMs can be defined, and per ESM, 20 AMFs can be defined. These ESMs can be switched either in the background application or programmatically in the robot application. Once a safety function of the active ESM state is violated, a safety stop is triggered. Now that we have a preliminary understanding of AMFs, PSMs, and ESMs, let's dive into Sunrise Workbench. Go ahead and open up the safety configurations file within your project. We'll be working in the customer PSM for the time being. Now, the customer PSM is the perfect place to put a safety baseline for your robot. For example, if you do not want the robot to exceed the hardware limits, you can put some software limits on the robot, which I would highly suggest. Or if you wanted to have a baseline for collision detection, such that the robot would never exceed, say, 20 Newton meters if it hits something, this would be a great place to put that baseline. Go ahead and add a new row to your safety configuration. Here we can change the category. The category is merely just an informational on what that safety row is about. So if we want to do a row about collision detection, we might choose a category that implies that the row is about collision detection. The AMF, I'm going to choose collision detection. And if you do not see these other AMFs in here, you will need to add the human-robot collaboration option package and or the safe operations option package in your station setup.cat. So for here, we're going to select the collision detection for our AMF1, and let's say we want the baseline to be 25 Newton meters of torque. Now notice if I click on AMF2 or 3, it says any unused cell is always violated. So right off the bat, 2 and 3 are automatically violated, and for this entire row to be violated, they all have to be violated. So the only thing that needs to be violated is for the robot to exceed a max external torque of 25 Newton meters. Lastly, we can also put a reaction on this row. So we could add a stop 0, a stop 1, etc. Or we could trigger a safety output. We could change the safety output over here. Now we have a couple different options for a safety output. We have an X11 interface on the robot controller, which is the discrete interface. And we could set those here, the SIB SR. We could also set a Profi-safe byte and or a failsafe over Ethernet byte. Now to set a failsafe over Ethernet byte or a Profi-safe byte, you will need to configure those safe bytes within Work Visual, not Sunrise Workbench. But for now, we could just choose a safe output. But for a collision detection, we might want to actually just stop the robot from continuing on. Now let's do one more example of setting like a software limit on an axis. So let's say we want to make sure that axis 7 does not go past negative 120 or 120 degrees. We can go ahead and add a new row over here. Let's say that this row is about workspace monitoring. And AMF1, we're going to choose the option for axis range monitoring. Here we can choose axis 7, and we're going to type in negative 120 degrees and 120 degrees. And as I change those values, you can see the graph also changes, which is a great visual representation of the range of motion for that axis, or the acceptable range of motion. So now if I were to actually save and synchronize this project to the robot controller, as long as these rows are activated inside the safety configurations, your robot would do a stop one reaction if you push on the robot more than 25 Newton meters. Additionally, the robot would also stop if you were moving the axis or trying to command the axis 7 past your range of negative 120 and 120. Now let's talk about ESMs and how they can be programmed inside of the application layer. As mentioned before, ESMs are a great way to monitor safety states in certain instances. So for example, we are already monitoring the maximum external torque of 25 Newton meters on the robot. And let's say we're planning on inserting a gear inside of a gearbox and we're worried about J7 exceeding the max torque. And we want to be more sensitive of the torque on J7, but only when we are inserting the gear inside of the gear set. This would be a perfect opportunity to use an ESM. So let's go ahead and create a new ESM by creating a new tab. We can click on our AMF and say axis torque monitoring. Here we can set the monitored axis to J7 and our min and max torque to negative 20 and 20 Newton meters. Additionally, we can also define our reaction. So here, when ESM 1 is on, we'll be monitoring axis 7 torque to make sure it doesn't go above or beyond our 20 Newton meter limit. And if so, we'll have our stop one reaction. Now, it's extremely important to note that if you have an ESM tab, there must be always and only one ESM active at a time. Therefore, if we save and synchronize the project, you will see that ESM1 is actually active, and there is no way to turn it off programmatically, which means we'll need a second ESM. Now, for our second ESM, we're not going to put anything in here except for an input. And the input, we're just going to jumper on the X11 to make sure that it's always high. This is just a way to get around having one ESM always on. So that way, when we're not wanting to monitor J7, we would just turn on ESM2. And then when we want J7 to be monitored, we would then turn on ESM1, monitor the safety. And then once we're done inserting our gear, we could turn on ESM2. And ESM2 will never actually trigger because our input signal in our X11 would just be jumpered to always being high, so it would never be low. Now, to actively set our ESM states in our application layer, we need to programmatically access the IControllerSafety interface. So here we can @inject the IControllerSafety, and we'll just call it ControllerSafety. Now let's say we want to set ESM to as our default ESM. Since it's monitoring really nothing, this has been jumpered high. This is the default just so that ESM1 isn't always on. So here we can initialize controller safety and we'll just set it equal to the ESM state 2. The set ESM state method takes in a string and it's just the number of the ESM that you want to set active. So in our case it's 2. Now let's say later in our application we are doing some gear insertion process, right? And we want to now actively set ESM state 1 since that's the ESM that is monitoring our J7 for a max torque. So here, it's as easy as just accessing the controller safety object and saying set ESM state, passing an ESM1 into the parameter, and just like that, we are now monitoring ESM1 for a overtorque on J7. The last topic that I would like to discuss is the concept of a muting button. The muting button allows us to recover from violated AMFs. It's essentially just a button or an input that is always low, which is always violated, and then to mute the violated safety row, we can press the button, creating a high signal which will suppress the row until the muting button is released. This muting button can be extremely useful, for example, when trying to recover from exceeding a joint limit. So let's do a quick example. So in our customer PSM, row 2 in AMF2, let's go ahead and add in a muting button. We can select the input signal as our AMF2, and then we would just make sure that the button is connected to the correct input. Make sure that the button is low so that it's always violated, so that when our robot passes the maximum or minimum allowable axis range, it will actually violate that safety row. And then when we press the button would go high, which would suppress or mute that safety row. Now be careful when using a muting button. So for example, in this instance, we're just merely passing a joint limit. So a muting button makes a lot of sense. But in the case of a collision detection, you may not want to put a muting button because there could be a lot of potential energy stored up in the robot from a collision. Best practice would be to go to the smart pad, flip the switch, put it in KRF mode, and incrementally jog the robot out away from the collision to diminish any potential energy that could be stored up within the robot. With all of that, this will conclude the safety configurations portion of this tutorial video.